Well, it's a genuine pleasure to introduce Time to you. This is when I first heard that he was doing a presentation like this, originally scheduled, as I recall, right time for the MOS conference that would have been down in Solomon's.
Yeah.
Is that right? Yeah. And that flooded out, so we have the conference being rescheduled down in Salisbury, I think it's August. And that should be nice. Should be here on the shore and be hot. Should be lots of fun. But Time, I knew him when he was knee-high to a knee. He and his sister were introduced to us in our Shinka team on their first YMOS trip, now probably 5 or 6 years ago at least. Time has since come and surf fished with me a couple of times. And last year, he and his sister came down for a weekend and with his family, and we crabbed. So I'm doing my best to corrupt him. But when it starts to look like BirdNET-Pi, I'm not sure I'll be able to do that. Time is a member of the YMOS, and that's certainly where I met him. But he also is a ninth grade. That's right, ninth grade student in the Science and Mathematics Academy at Aberdeen High School up in Aberdeen, Maryland. And he's going to talk today about the interface, if you will, between technology and birding for a better approach to acoustic monitoring. Time, welcome.
Yeah. Hello. Can everyone see my presentation screen?
Yes. Yeah.
Okay. Yeah. So yeah, thank you again to Dr. Bell and Miss Trina for letting me present to you guys. I'm so excited. So today I will be talking about my presentation and project called Rethinking BirdNET-Pi, a technical approach to better bioacoustic monitoring. So like Dr. Bell said, I'm a ninth grader at the Science and Math Academy in Aberdeen, Maryland. So I have been birding for 10 years now. In my county, I am the trip leader and newsletter editor of the Hartford Bird Club, which is my local chapter. And I'm also a member of the Youth MOS chapter. So this picture is me years ago, maybe 2019 at Blackwater Refuge. So this is me and this is my sister. So yeah, we do bird as a family and we've been doing that for all these years. And now this is me today. This was actually taken on Saturday. We were at a trip at Susquehanna State Park. So if you guys love birds and if you guys love flowers too, this is the time of year to go because all the flowers, like the Virginia bluebells here, are all blooming now. Okay, so let's talk it. Let's get in. So what will we talk about today? So what is BirdNET-Pi and bioacoustic monitoring? And why does this all matter? And then how did I conduct an experiment with this technology? And how is AI and technology revolutionizing the birding world? So let's get in. So what is BirdNET-Pi? BirdNET-Pi is an open source bioacoustic monitoring system or code that runs on this mini computer called a Raspberry Pi. Can you guys see from my
Yes.
camera? Okay, yeah. So this is a Raspberry Pi. It's basically a mini computer that can run all sorts of different things like BirdNET-Pi. So BirdNET-Pi uses a machine learning model, which is the same one that was trained for Merlin Bird ID, and it can be used to identify 984 North American and European bird species by their vocalization. So this technology can be differentiated from Merlin Bird ID because when it records each environmental sounds, it processes it by ignoring all the non-bird sounds that it records, such as construction noise or car noise from the road, and then it identifies only the bird call. Now, this system also has a global network called BirdWeather, and this is an interactive map of any live BirdNET-Pi installations that are posted to it from around the world. So this technology has a computer interface. I will be showing this. So it displays a spectrogram, which updates every 15 seconds. That looks like this. And then a list of the 5 most recent detections and this displays the species detected in common name and scientific name and the confidence level. Now, confidence level is basically the probability in percentage that each identification is correct. So like on this identification, the system is 60% sure that this was a northern cardinal vocalization. So some pros of this technology is that it is low cost and also automatic. So it can work offline in remote situations. But this technology is limited because of the types of microphone and also background noise and any environmental interference. So I'll be showing this interface now. Do you see my screen changed?
Yes.
Okay. So this is the user interface for BirdNET-Pi. So it shows you some stats, like which type of species that it's recorded and the counts of each identification. And then if you scroll down, this is like that spectrogram that I showed you. So it shows you what species it is, and then the confidence level. Again, that is basically the probability that it is correct. So a spectrogram is a graph of a sound. So what it does is that it graphs frequency, which is like the pitch. So a lower sound like this, and then is on the lower scale, and then a higher sound like this is up higher. So in this northern cardinal, we can see that its vocalization is made up of mostly low whistles and somewhat high, sharper noises at the end of each whistle. And you can also play back each vocalization to hear it, like this. Yeah. Can you guys hear that?
Yeah. Yes.
Yeah. Okay. And then if you scroll down some more, it shows you the 5 most recent detections. So cardinal, and then the species detected, the confidence level, and then you can also play these back. So now this is the current spectrogram that it's analyzing. So it's using this microphone here to get this noise. So it updates every 15 seconds, which is why it is not moving now. So I will play a cardinal vocalization and then see if it can identify it correctly. Yep. So as you can see here, this is that vocalization that I just played. And if we scroll up, it should see, yep. So this was the identification that it just recorded. So it was able to tell it was a northern cardinal. It also tells you the time that it recorded the identification. And then in this specific case, it was 55% sure that it was correct. Yeah. So here, I'll try one more species to see if it can ID that correctly too. So let's try the fish crow. Okay, so now if we go to our spectrogram, we should be able to see something else that shows up. So this kind of jumbled spectrogram noise is talking. So now these four sounds should be that fish crow call. So if we wait up here, should be able to record them. We might have to wait a little because of the reset time. Or not. Maybe not. Yeah. Okay. Here, I'll try one more then. Let's see. Do you guys have suggestions? Something distinct.
White-throated.
White-throated sparrow. Okay. Yeah.
Good ones.
So now if we see, here is the call showing up. So let's see if it recorded that one. Yep. So here we go. So it was able to record that one, but at a somewhat lower confidence level. So we can see that showed up in our recent detections also. Yeah. Okay. Do you have any questions so far about this interface?
I have a question. You said it uses the same learning model as Merlin, but it's not using Merlin though itself. Is that
No,
correct?
it is. So it uses the same learning model. So the same learning model was trained to use for Merlin Bird ID and BirdNET-Pi, but they have different technologies or applications that they're used on. So like Merlin ID is a mobile app, and the interface is like on the phone, and it is more somewhat interactive. So you can start the recording, but then BirdNET-Pi is somewhat different. So it is run on not a mobile device, but a Raspberry Pi.
Does it use the same data as Merlin though? The same like the Cornell lab?
Yes. Yeah, it uses the same data. So both of the models were trained based off of the Macaulay library. So yeah, it is the same model, but they have different operating systems. That's what differentiates them. Yeah. And then this Raspberry Pi, so the purpose of using a Pi is to make it affordable. So it's just $50. Yeah. Okay.
You mean as opposed to the cost of an iPhone or something?
Yeah, you could say that. Yeah, but then yeah, you would need a microphone too to record sounds. Okay, so now that we know what this technology and BirdNET-Pi is, let's talk about bioacoustic monitoring. This is a scientific technique that allows scientists to use biological sounds to detect wildlife and assess the quality of ecosystems. It allows them to secretly analyze, monitor population trends and track any environmental changes in the area. So some current examples of bioacoustic monitoring are conservation, to evaluate the recovery of a habitat after it's damaged by a disaster. Scientists also use this in the ocean to track whale and dolphin migration by recording their marine calls. And then they also use this to monitor endangered bird and bat species based off of their vocalization. So what we can see in this picture is a Terra biostation. So this is like a public and commercial version of the BirdNET-Pi that you can actually purchase and just put in your backyard. And this is what that BirdWeather network uses to make the global database for BirdNET-Pi. Now, why does this technology matter? So it allows us to monitor birds constantly 24/7 so that birders and scientists don't have to wake up in the middle of the night again to go find a needed bird. And instead, this technology can do it for them. It is also a cost-effective way to study bird populations secretly and without interfering with them. So this is important in the Middle East, as scientists are using bioacoustic monitoring to study breeding populations of common terns and least terns. So now let's get into my project. So BirdNET-Pi is effective and affordable, and it can be used to automate this acoustic bird identification, but it is limited by factors such as poor audio quality, background environmental noise, and feedback noise from the microphone. So improving the quality of the captured sound from the microphone is essential to make BirdNET-Pi more reliable for real-world situations. Now, in my project, I wanted to keep my materials on a budget, and instead of just choosing that expensive microphone, I went with these like $20 wireless lavalier microphones, and then an affordable $50 Raspberry Pi to use for my operating system. So my hypothesis was that using a paraboloid or sound enhancing structure will enhance the microphone and cause it to capture sound better at various distances and angles. And this will increase the system's average confidence level and the accuracy of its species identification. So in this test, I used parabolic microphones. And parabolic microphones use parabolic reflectors like this. So these reflectors can allow you to focus sound from one direction onto one central microphone. So how how this looks like is that the microphone is pointing inwards towards the dish. And as we can see in this diagram, as sound waves hit the dish, they bounce off the curvature of the walls and they bounce onto one focal point, like here on the microphone. Now, these dishes are not only used for sound, they're used in like satellite dishes too. So the parabolic shape of a parabolic dish collects the sound waves and then reflects them towards that focal point. And this amplifies each signal of the sound and increases the sensitivity of the system. Using this technology also reduces the background noise because it doesn't amplify any background noise, so which results in a cleaner recording and better sound quality over a omnidirectional or 360-degree microphone. And parabolic microphones also have a higher signal-to-noise ratio. This is the ratio of the desired sound, like the bird vocalization, to the background noise over any other microphone, which results in a more distinct bird vocalization with less background interference. And this will make the system more accurate. So these are the, I've used 4 in parabolic reflectors. So the first 2 are circular. This is the large paraboloid, which is a 13-inch diameter dish, and it is made out of 3D printed plastic. I also used the small paraboloid, which is an 8-inch diameter dish made out of clear plastic. Next were the rectangular reflectors. So this is the large reflector, which is a 12.3 by 8-inch rectangle made out of 3D printed plastic. And then the last one was the small rectangular paraboloid, which is a 7.4 by 4.inch rectangle, which is also made out of 3D printed plastic. So I conducted 2 main tests using these materials. So first is that Raspberry Pi, and it also has a wireless receiver for the lavalier microphones that I used. The next setup was the laptop and monitor to display the interface for the BirdNET-Pi and my iPhone, which I just used to play the bird calls. And the next is the stationary parabolic microphone, which includes the wireless microphone, the wireless microphone, and each parabolic reflector. And then the last step is that I used a speaker to play the bird call. So the point of using a speaker is to create a standardized signal, which results in the bird call playing at the same volume in each test. And then I move this around the room to conduct each test. So let's. Okay. Are there any questions so far? Okay. So the first test that I conducted was the distance test. In this test, I wanted to see how playing a sound at a higher distance would affect the accuracy of the system. So in this test, I kept the microphone and paraboloid stationary in one place. So the paraboloid dish was pointing outwards as indicated by this arrow. And then I moved the speaker, which played the sound towards the parabolic reflector. So first I started it at 5 feet and then I moved it back in 5-foot increments all the way back to 35 feet. And at each of these 5-foot distance markers, I recorded the confidence level of 10 identifications at each distance, and then recorded the average to determine the effectiveness of the paraboloid at each distance. So the next test I conducted was the angular tests. And this test is similar in that the microphone and paraboloid are also stationary, and then they're pointed outwards, but now towards this 0-degree marker. Now the speaker was always kept 10 feet away from the microphone in all parts of this circle. And then I moved the speaker, which always played the sound towards the direction of the microphone in 30-degree increments around the circle in a counterclockwise manner. And then at this time, in this test, I recorded the confidence level of 10 identifications at each angle. So let's get into the data and results that I found. So starting with the distance test, this line shows the average confidence levels of 5 to 35 feet of the baseline, and the baseline was only the microphone. So this had no reflectors attached. So as we can see, starting at a closer distance, the confidence level is higher, about 85 or 86%. But then as the distance increases, the confidence level decreased all the way at 35 feet up till about 43% confidence. Next, we can add the small paraboloid, which is the clear circular dish, this one. So as we can see, the average confidence levels were significantly lower than that of the baseline one, which is just the microphone. The next one was the large paraboloid, the white circular dish. So in this test, we can see the same trend. So as the distance was lower, confidence level was higher, but then as we increased distance, confidence level decreased. But this test, the confidence level decreased at a slower rate than the others. Now we move on to the rectangular dishes, starting with the small rectangular paraboloid. So the confidence levels for this, using this paraboloid, were somewhat in the middle of the range. And then lastly, with the large rectangular paraboloid, this one was different in that because it started lower, and then as distance increased, it stayed somewhat constant and then even increased a little. So as we can see from these tests, as the distance increased, the confidence level generally decreased. Now, the best dish that I recorded from the average confidence levels was the large paraboloid, which is shown by this purple line. So the average confidence levels were generally higher than all of the other ones, which is why I chose it as the best. Now, the worst dish was the small paraboloid, the small clear rectangular one, circular one, sorry, because its confidence levels were generally lower than the others, and the confidence level decreased at a faster rate. Also, when the distance was past 30 feet, the identifications were too distorted, and it could not even identify the call correctly, which is why there is no point at 35 feet for the small paraboloid. Now let's look at the results for the angular test. Starting with the baseline again, which is just the microphone. As the angle from the microphone was closer to 0, confidence level started higher at around 79%, and then generally decreased at 180 degrees from the microphone, which is pointing to the back of the dish, and then that confidence level was around 36%. Now, adding the dishes, starting with the small circular paraboloid, these confidence levels were somewhat more constant than the baseline, but they were generally lower. Next, we add the large paraboloid. These confidence levels were somewhat equal, or higher than the baseline. Now going to the rectangular dishes, starting with the small rectangular paraboloid. Again, these confidence levels, similar to the distance test, are in the middle range of all of the others. Then finally, with the large rectangular paraboloid, these confidence levels were somewhat equal, but then not as high sometimes as the others. So as we can see from this test, as the angle from the source of the sound, so the speaker, increased, then the average confidence level of the identification decreased. So these confidence levels are somewhat similar. So I chose the one that was somewhat higher than the other ones. Again, the large paraboloid, the large circular paraboloid. And then the worst overall was the small paraboloid again, because its confidence levels were significantly lower, were always lower than the confidence levels of the other dishes. So from these two tests, the best overall parabolic reflector was the large circular paraboloid, because it had the highest average confidence levels in both tests. And this could be because it has a larger diameter than the others, which allows it to capture more sound from the source. The wide circular shape also allows it to capture a narrower and more condensed sound, which allows more distant detections and higher confidence in each identification. This is because of its even circular shape, which results in a more condensed focal point at the microphone. Now, a circular shape is better than a rectangular shape because rectangular dishes have an uneven curvature compared to a circle, which might spread out the sound, and then the corners of it could scatter out the sound waves. This causes it to have more distortion in the sound, which decreases the accuracy of each identification. So some steps that I'm planning to take in the future to improve this project is to conduct some more experiments, such as the same experiments, so the distance and angular tests, but with a higher and a lower frequency bird vocalization to see how the system and each parabolic reflector reacts and records each identification better or worse with a higher or lower frequency. I can also conduct these same experiments outside or at greater distances to add more variables to make it more like a real-world situation. Once my system is improved, then I can implement this into my community, such as making a weatherproof BirdNET-Pi station, such as this one. And then I can install this near bird banding stations to compare the digital bioacoustic data to the physical migration data recorded from the banding stations. And I can also install this station in the Otter Point Creek, which is a hotspot for SOAR rails to monitor secretive marsh birds there. So this AI technology is revolutionizing birding because it allows real-time sound ID at any time of the day when it has power. And these apps and technology allow people with little to no prior knowledge to join research and participate in birding. AI can also process very large quantities of acoustic data quickly and determine any shifting patterns and trends out of them to see if populations of specific species are increasing or decreasing. And these recognition AI stations off the grid can also automatically monitor species that human scientists and researchers might miss. Even though this technology is revolutionizing birding, it still has some limitations. So this technology is still somewhat new, so it is not perfect yet. So it can still produce some false positive identifications, especially in noisier environments. So it should only be used as a supplement, and it shouldn't fully replace human verification of any species identifications. So considering the habitat and behavior and visual observations, like in a normal real-world birding situation, are critical to record accurate data using AI and technology. Yeah. Thank you for listening. Are there any questions about the project?
I do have a question. So thank you. I think that was very impressive. I really enjoyed it. Did you make your 3D speakers? You said the rectangular ones were 3D printed.
Yes. So I didn't create them using like a 3D software. So I took them basically off the internet, and then I made the sides. I made the size increased or decreased for the different tests. So for the rectangular paraboloid, I took an online file of that dish. And then, so for the small paraboloid, I just shrunk it down on the printing software. And then for the large dish, I just made it into this size by increasing the size of it.
You used a 3D printer.
Yes. Yeah. And then once I figure out what shapes and what sizes of dishes work best, then I can customize it and then create a dish myself to create on a 3D printer.
Good question. When you use the spectrogram, is that like a fingerprint for each bird that will follow a certain print spectrogram?
Can you repeat that again, please?
Talk a little bit louder. The spectrograms look to me as an artist like a picture. So is that what is how you identify what bird it is? It's like a fingerprint, that each one of us have a different fingerprint, and these birds have
yes. So yes. So the spectrogram is like a picture of each bird call. So that is how it is trained to identify each bird call from another. So looking at this call, it is different. So you can see that this call is different from, say, this one. And then that is how it can tell between these species. So as you probably know, each species has a different and its own distinct call. And then, this model is trained to identify them based off of the spectrogram. So it's a picture of the bird call, basically.
like a fingerprint.
Yeah, a fingerprint to identify it.
Thank you.
Yeah, I have a
question that is maybe built on what you ask. Some birds have very similar pattern, right? Are you planning to introduce some of these birds in your experiment to see how well you separate them? Because I'm assuming you need to have a visual to confirm that it's one species versus another species if the sound is very similar.
Yes. So yeah, my plan. So yeah, since there are birds with like similar calls, my plan is to conduct these experiments again, but with say 2 different species that have similar bird calls. And another question that I brought to mind was mimics. So like your mockingbirds and thrashers, such as like how can this technology tell that like a bird calling is a mimic and not the bird that it is trying to imitate?
Can I suggest another one?
Yeah.
I have asked Dr. Bell to perform this speech rule. Because Merlin picks that up as a script show.
Seven screech owls. Time to, is BirdNET-Pi able to distinguish chips as well as songs, or is that a lot tougher?
Well, on spectrograms, the chips look a lot more similar than they might sound. So yeah, it is less accurate at identifying the chips over like the bird's distinctive song.
Can it do higher frequencies than we can hear? Because I've been involved in experiments where they're trying to find bats, and it shows up as a spectrogram and we can't hear anything, but we can see it, and then we can identify the species by looking at that.
Yeah, so yeah, the spectrogram is able to record like pretty high frequencies of sounds. So it goes up to 12 hertz. We can see 12K hertz. So like 12,000 hertz. And that is a pretty high frequency, maybe even more than some people can hear. So yeah, this technology allows it to record more. And this frequency is also dependent on the quality of microphone. So if you have like a cheaper microphone, like the ones that the ones I'm using for the test, they may not be able to record a higher frequency, but with using a sound enhancing structure like a parabolic reflector, those sounds might be more clear and allow it to identify and record those higher frequencies, even higher than like a human might hear.
How is this different from Merlin? What does this do that Merlin doesn't do?
So the BirdNET-Pi, so even though it runs off of the same system as Merlin, it allows you to like save your detections, and then it gives you statistics of your different detections. So it tells you like all of your species like collectively, and then like the number of recordings that it's gotten of all time. So like this system, my system has recorded 1,849. So say that's something that you can't really see on Merlin. And then there's also that global system, that BirdWeather network, which allows you to see other people from around the world who use this system, and then see like what types of species that they record.
Is it more accurate than Merlin?
I wouldn't really compare one as more accurate than the other because it uses the same system. Now with BirdNET-Pi, because it is an open source code, people can go in and change different things about it, which in some number of years, it might be able to be changed and then be even more accurate than Merlin. But right now, in my opinion, you can't really compare them based off of accuracy.
Thank you.
One of the things that I see here that I wish Merlin did have was that confidence level.
Mhm.
Because, you're talking about false positives and mimics. I was doing a bird walk at Blackwater a week and a half ago, and I had a mockingbird that in the middle of it kept on coming up as a greater yellow legs.
Yeah. Yeah, that is a problem of these AI and technological systems, because they might not like be so confident in recording things. So that is why Merlin might like record a mimic like a mockingbird as something that it is mimicking and not the actual mockingbird.
It almost seemed like it was working too hard to extract something out of a lot of a complex song. So
yeah, and the confidence level, like if you can look at it, you can like the birder can also determine if they want to like say that identification is true or not.
Right.
Are there plans for any of your contacts or colleagues to implement some of this summer at any particular location?
Well, I was thinking about working around like the parks in my county, so like Eden Mill Nature Center, Susquehanna State Park, because like Susquehanna State Park
Oops.
is a hotspot for migrating warblers, and I guess that will be effective in recording the migration there. And then there's also a bird banding station at Eden Mill Nature Center, so I can set up that station there and then compare the data that it records to the data from the physical banding station.
Wow, that could be done.
Yeah.
Good. Other questions? Absolutely fascinating. I bet this is going to continue to grow.
Thank you. Thank you.
Thank you.
Thank you, Tom, and best for your family.
Yeah, thank you for letting me talk here.
Okay, a pleasure.
Thank you. Best of luck.
You learned a lot.
Yes.
Okay, yeah, thank you. Bye.